Welcome. Today we shall discuss exoplanets, planets orbiting stars far, far away, but in our galaxy. The first exoplanet was interestingly discovered orbiting a millisecond pulsar. This discovery was made by the Polish radio astronomer Wolczan in 1992. It was a millisecond pulsar with a rotation period of 6 milliseconds. There are 3 confirmed planets orbiting this neutron star. 2 roughly the mass of the Earth, and the third has a mass roughly equal to the Moon. The first exoplanet system around a gaseous star was discovered in 1995 by Michel and Didier Queloz of the Geneva Observatory in Switzerland, orbiting the star 51 Pegasi. The mass of this planet was roughly 50% of the mass of our own Jupiter, but its size was 50% larger than the size of Jupiter. Its orbital period was astonishingly just 4 Earth days. Well, here it is. This is the planet. This is not an actual photograph, but just to give you a feel for it, this is the planet which is called 51 Pegasi B. Its size is 50% larger than Jupiter, and the star itself, 51 Pegasi, is larger than our own Sun. This discovery was profoundly important, and in 2019, the Nobel Prize for Physics was awarded to Michel and Didier Queloz for the discovery of the first exoplanet orbiting a gaseous star like our own Sun. Now here is a plot of the planets that have been discovered so far. What is plotted on the y-axis is the radius of the planet measured in units of the radius of the Earth, and on the x-axis is the orbital period measured in Earth days. So here is 10 Earth days, 100 Earth days, 1,000 Earth days, and so on. So you clearly see there are planets which are very close to the central star, the host star, and then there are planets which are very large compared even to Jupiter. There is the size of Jupiter, and which are at a very large distance from the star. As of September 2022, there are 5,157 confirmed planets in 3,804 planetary systems. Of all the stars that were studied, 830 stars have more than one planet. So multiple planets seem to be very common. Now, how are these planets detected? There are several techniques. They sound very simple, but they're exceedingly difficult. So let me at least mention what these techniques are. The first is direct imaging. Clearly, if you image the star around which there is a planet going around, then you will basically see the reflected light from the planet, whose intensity will be millions of times less than the brightness of the star itself. Therefore, you are unlikely to ever detect the planet. Therefore, what is done is inside the telescope, there is a little disk that blocks out the light from the star. Therefore, what you see is only light from beyond the star. This technique is used to study the corona of the sun, As you know, during total solar eclipse, you can see the spectacular corona. But astronomers don't wait anymore for a total solar eclipse to study the corona. Inside a telescope, they have a disk which blocks out the light from the sun. Therefore, you see only the corona. So you create an eclipse inside the telescope. Now, this is easier said than done, because even though you may block out the light from the sun with a disk inside the telescope, there will be scattered light, and the scattering inside the telescope. And that intensity of the scattered light can far exceed the intensity of the solar corona, in this case, the orbiting planet. Therefore, this technique, although it's very simple to state, is very difficult to achieve. The second technique is what is known as the transit method. And the third is what is known as Doppler method or radial velocity. And the fourth, there are so many other methods, including micro-lensing due to gravitational lensing. So let me say a few more words about the first three of these techniques, because they are the most common. So here is a star that has been blocked by a disk inside the telescope, and what you see is only the planet. This is obviously an image taken in the infrared, because the planet is more likely to radiate in the infrared. Here is another star that has been blocked out, and you see three planets orbiting the star, planet B, C, and D. So this is the technique of direct imaging. It is exceedingly difficult, but astronomers are now routinely doing this. The second technique is the following. If by chance the orbital plane around this host star has a favorable geometry, then you can see the planet transiting the star. Therefore, what you try to do is to measure as accurately as you can the brightness of the star as a function of time. So clearly, as the planet enters the disk of the star, the intensity will go down, and then at the end of the transit, the intensity will be back to the normal level. So this is the transit method. Now please remember that when a small planet goes in front of a star, we know that the transit of Mercury and Venus have been studied for centuries. In fact, Captain Cook came to India for the famous transit of Venus experiment. But on the other hand, here we are talking about a very distant star, many, many light years away. Therefore, the photometric accuracy of your detector has to be incredibly large in order to be able to detect a very small dip in the intensity of light as the planet transits the star. The third method is known as the Doppler technique, and it's a very simple method, and indeed it is this technique that was used to detect the planets around the pulsar, the very first extrasolar planets. So what I have shown here is a central star, that is that one there, where my cursor is located, and then there is a planet orbiting the star. So what you're not trying to detect the planet. What you're trying to detect is some spectral line, say the H-alpha line of hydrogen, emitted by the star. Now, if the star was stationary, then the frequency of that H-alpha line will be fixed. But the star will not be stationary if there is a planet, because if there is a star and there is a planet, there is a common center of mass. And since the mass of the star is very much greater than the mass of the planet, the center of mass will be very, very close to the star itself. It may even be inside the surface of the star. But nevertheless, the star, unless its mass is infinite, will also be going around the common center of mass. Right? Now this motion will be a very slight motion. But because of this motion, the frequency of the H alpha line, for example, that you're trying to detect from the star, will show Doppler modulation. All right? If the orbit is such that the star is moving towards you and away from you as it is going around the common center of mass, you will find the H alpha line to be blue shifted, red shifted, blue shifted, red shifted, and so on. Now this shift will be very, very small. Please remember the Doppler shift, delta lambda over lambda, is equal to V over C, where V is the velocity of the star around the common center of mass, which is very, very small. But astronomers are very good at measuring very small velocities because of high dispersion spectrographs. So here, for example, is a measurement of the wavelength of some light emitted, radiation emitted by the star as it moves around the common center of mass. And you see that the wavelength is modulated sinusoidally, just as you would expect from simple Doppler argument. So this is how you infer the existence of the planet. You don't directly detect the planet, but you infer the existence of the planet from the fact that the star is moving around some imaginary point. This is what can be done far more accurately with the pulsar. Now, if the pulsar was stationary, then you would expect the pulsars to come at periodic intervals. But because there are planets going around the pulsar, 3 planets, the pulsar will be going around the common center of mass defined by this 4-body system. But radio astronomers can measure frequencies incredibly accurately. So that is why within 4 years, Volchan and Dale Frail were able to say there isn't just one planet, but there are actually 3 planets, maybe even 4 planets orbiting the 6 millisecond pulsar. So this is the third technique which is used. It is this technique that was used by Michel and his collaborators for the discovery of the very first extrasolar planet. As I said, that planet was almost as big as Jupiter, and therefore this motion, Doppler motion of the star, could have been significant. In 2009, NASA launched a satellite for detecting planets, in particular, planets roughly the size of the Earth. And this satellite was named after the great astronomer Johannes Kepler. So this Kepler satellite has been enormously successful in detecting new planets. The main technique it uses is the transit light curve that I had mentioned earlier. Here are 5 planets discovered by the Kepler satellite, and you see here the actual light curve during the transit. So, well above the level of the noise. The signal to noise ratio is outstanding in these observations using the Kepler satellite. Now, these 5 satellites have different orbital periods, around 3 to 5 days. So here is once again a plot of the known planets, some 5,000 or so known planets. Not sure all of them are in this plot. What is plotted on the y-axis now is the mass of the planet in units of mass of our own Jupiter, and on the x-axis is the orbital period. So that is 1, that is the mass of Jupiter. So you see that there are planets which are less massive than Jupiter over here. And then there are planets which are more massive than Jupiter, 10 times, 20 times, 30 times the mass of Jupiter. Clearly, there are more massive planets with larger orbital periods than smaller orbital period. This is something I will come to towards the end. So there are the massive planets with large orbits, there are the massive planets with smaller orbits. Now, one of the remarkable things that has been noticed by astronomers is that there is a very large number of planets whose size is between the size of the Earth and the size of Neptune. Here is Mercury, Mars, Venus, Earth, Uranus, Saturn, Jupiter. So in our solar system, there is nothing between Earth and Neptune or Uranus in size. There are planets. There's Mars outside the Earth's orbit, but Mars is even smaller than the Earth. So what is noticeable from this data is that there are very large number. Please notice the number. We're talking about 1,600 and so on. Very large number of planets whose sizes are between the size of the Earth and the size of Uranus and Neptune. I don't know how many of you know the story of Goldilocks and the three bears. This is Goldilocks. She's walking in the forest and stumbles into a little cottage. There was nobody in the cottage. There was a table with 3 bowls of porridge. She tasted the big one, porridge in the big, it was too hot. Then she tasted the porridge in the medium-sized one. That was too cold. Then she tasted the porridge in the small cup. That was just perfect. It was neither too hot nor too cold. These 3 bowls, of course, belonged to the father bear, the mother bear, and the baby bear, which had gone out for a stroll. So that is the story of Goldilocks and the 3 bears. Now, why am I bringing Goldilocks? One of the things that astronomers were interested in was to see if any of the planets orbiting other stars are at a distance such that essential ingredients for life obtained in those planets. Life, as we know on Earth, requires water and hydrocarbons. So that region, if it's too close to the star, it will be too hot. If it's too far from the star, it will be too cold. So it has to be a region in between, where conditions like the conditions that obtain on Earth might possibly exist in extrasolar systems. And that region was originally called Goldilocks region. But astronomers have redefined that region as habitable zones. So here is a plot of planets and candidate planets discovered by Kepler in the habitable zone. What is plotted on the y-axis is the surface temperature, and what is plotted on the x-axis is the energy received by the planet from the sun. So this is the Goldilocks region. And interestingly, many planets, these blue are confirmed, and yellow are new candidates, and white are candidates which are not yet confirmed. So many planets have already been found in the Goldilocks zone or the habitable zone. And these will, of course, be intensely studied using the James Webb Telescope, where there is a spectrograph to study the atmosphere of extrasolar planets. And now we come to the key question: how do planets form? And I have a confession to make right at the outset. This is a new subject, and it's an exceedingly complicated subject, and the dust has not settled down, no pun intended, as you will see. And I have not studied this subject before, except watching it on television or reading about it in newspapers and magazines. So almost everything that I am speaking about in this lecture, I sat down and tried to learn for the purpose of recording this lecture. Therefore, my understanding so far of how planets form is very minimal. So you have to keep that in mind. So what I shall try to do is not try to bore you with details, which I don't understand in any case, but try to highlight the principles which astronomers are focusing on, physicists and astronomers are focusing on to form planets. This is Giordano Bruno, an Italian mathematician, philosopher, poet, and cosmologist. That period was, of course, the time of the Renaissance in Italy, the time of Leonardo da Vinci, Michelangelo, Brunelleschi, Botticelli, and so on. So that time, there were many people who were like Bruno, who were mathematicians, cosmologists, and you name it. Now, astonishingly, 500 years ago, Bruno proposed that stars were distant suns surrounded by their own planets. Please remember, the sun is a big object. Stars are point-like objects. Nobody before Bruno, as far as we know, had asked the question, are the stars like our sun? So Bruno was the first person to ask the question. He not only answered it by saying, yes, stars were distant suns, but he conjectured that they must also be surrounded by their own planets. Then, of course, come to Newton, concluding his monumental book, the Principia, he wrote, and if the fixed stars are the centers of similar systems, they will all be constructed according to a similar design and subject to the dominion of one. Well, what he meant was the following. One of the questions philosophers were arguing at the time of Newton was the following. Is the sun a star? It looks very different. Newton dismissed this question by saying, of course the sun is a star. The other suns are looking small because they are far away. But then he went on to ask, like Bruno, are they centers of similar systems, similar planetary systems? And then he went on to say, if they are, then the laws of physics, which will govern the motion of those planets, will be the same as the laws of physics that he had written down in this book, Principia. Please remember, when he formulated the law of gravity in this book, he stated, every body in the universe attracts every other body according to ... So he asserted that the laws of physics are of universal validity. So here is the statement by Newton. Very strong statement. This is Pierre-Simon Laplace, the great French mathematician. He was a great teacher, and Napoleon Bonaparte was one of his students before he became emperor, of course. Now, the great mathematician Laplace was struck by the fact that all the planets in the solar system are in a plane. All right? Why are they in the plane? Nobody had asked this question before. He conjectured that planets might have formed from a flattened disk that surrounded the sun when the sun was very young. Of course, there is no such disk around the sun now, but he conjectured that when the sun itself was formed, when the sun itself was young, that there is again a very profound statement. So he asserts that the sun was born at some time. It didn't exist forever. There might have been a flattened disk from which the planets formed. Absolutely remarkable conjecture. By the way, this may be relevant when we discuss cosmology starting in the next lecture. There one is confronted with the question of whether who created the universe. Did God create the universe? So Laplace, when he published his famous book on mechanics, presented a copy to Emperor Napoleon, who was his former student. Napoleon looked at the book for some time and asked Laplace, but Professor Laplace, there is no mention of God in your book. And Laplace replied, Sire, I have no need for that hypothesis. So I shall come to this in the last lecture of this series. So that was LaPlace making this most remarkable and prescient conjecture. What I've shown in this picture are disks of gas and dust surrounding young stars, exactly as LaPlace had conjectured centuries ago. These are actual observations done with a giant millimeter wave interferometer known as Alma, Atacama submillimeter wave interferometer. It consists of a large number of extremely sophisticated antennas, all working in unison using the aperture synthesis technique, about which I spoke when we discussed radio galaxies in one of the earlier lectures. So this telescope is located on top of the Andes Mountains in Chile because you are doing submillimeter wave observations, and molecules emit submillimeter wave observations. There are a lot of molecules in Earth's atmosphere which will absorb this radiation, so you want to go as high as possible. Now, this remarkable telescope built by the European Southern Observatory made these observations. So here are some more disks of gas and dust seen in the sub-millimeter wave region by the Alma Interferometer, exactly as LaPlace had conjectured many centuries ago. Now let's go back to the very first planet discovered by the Polish astronomer Wolfson around the millisecond pulsar. I still don't understand why he was not awarded the Nobel Prize along with Michel and Didier Queloz, because after all, he did detect the first planet. Now, the first exoplanet, as I said, was discovered around the millisecond pulsar, the 6 millisecond pulsar. Now, if you recall my lecture on millisecond pulsars, the understanding is that millisecond pulsars are born in low mass X-ray binaries, LMXPs, and they are spun up to very short periods by accreting matter from an accretion disk. This was a conjecture that we had made at the Raman Institute within days after the millisecond pulsar was discovered way back in 1982, 40 years ago. But today, as I showed you in my lecture on millisecond pulsar, there is a concrete proof of this. We have seen a half a dozen low-mass X-ray binaries which switch on and off in X-rays. And when it switches off in X-rays, you see a radio millisecond pulsar right at the center. And these pulsars are being spun up to millisecond period by accretion from an accretion disk for roughly 100 million years. So here is an actual proof, a best direct evidence so far that planets do indeed form from a disk made of gas and dust. So in my opinion, this is a smoking gun, as it were, for the theory that planets form from a disk of gas and dust surrounding the host star, exactly as LaPlace had conjectured centuries ago. Now, here is a remarkable fact. That is a young star cluster, Pleiades. In a young star clusters, observations tell us that most stars have gaseous disks with a lot of dust in it. Such disks are absent in older clusters, but they are present around most stars in a young cluster like Pleiades, Hyades, and so on. The disk typically lasts for a few million years and then it disappears. Now here is a plot of the fraction of stars which have disks as a function of the age of the stars. So you see, as you look at older and older stars, the fraction of stars having a gaseous disk becomes smaller and smaller and smaller. So this is the basis for saying that the disks around newly formed stars last only for a few million years. So a few million years is all the time that you have to form planets. Here is a disk around a star seen by Alma. Now, from sub-millimeter observations, you can deduce the masses of the disk, the mass in the gas plus dust. And what these observations tell us, that the masses of the disk are typically 1% of the stellar mass. So if the star has a mass similar to the sun, then 1% will be 10 to the power 33 or 10 to the power 32 grams, still a very large number. Alma has sufficient angular resolution, as you see here in this image, to map the disk beyond 10 or 100 astronomical unit. What is an astronomical unit? That's the distance of the Earth from the Sun. 150 million kilometers from, we are 150 million kilometers from the Sun. So that is one astronomical unit. So Alma can map the circumstellar disk, not very close to the star, but at some distance from the star, say 10 to 100 astronomical units. From these observations, astronomers have deduced that the surface density of the dust falls as 1 over r. When I discuss the population of stars in the disk of our Milky Way galaxy, I said the same thing. As you go away from the center of the star in the disk of the galaxy, the density of stars goes down as 1 over r. In this case, the density of gas and dust, the surface density, goes down as 1 over r. The matter from the disk accretes onto the star, like an all accretion disk around neutron star, black holes, and so on. Why? Because, well, we'll come to that. Well, let me tell this and repeat that once again. The gas in the disk rubs against each other. There is friction, there is viscosity, and therefore the particles lose energy. If the particles, let us say a particle is orbiting the star according to Kepler's laws, it has to have a certain angular momentum. If I slow it down, then its angular momentum becomes less. Therefore, it has to come in. All right? So that is how, as long as there is viscosity in the disk, the matter in the disk will eventually come and fall onto the central body. That is how a neutron star is spun up in a binary system, in a low-mass X-ray binary or massive binary. Now, before we discuss ideas that astronomers are playing around with today for the formation of planets, let us remind ourselves of the constraints on such theories that come from this very large number of observations of exoplanets that have already been made. You can't sit and, like Einstein invented the general theory of relativity in vacuum, because at that time there were no known violations of Newtonian gravity. So Einstein could simply sit in a rocking chair and think of a theory and worry about confirmation of the theory later on. But here we have 5,000 planets that have already been discovered. So what are the constraints on theoretical scenarios that emerge from this observation? I will simply list them without going into the details. Radial velocity surveys, that is the Doppler velocities that I told you, show that gas giant exists in 10% of the sun-like stars. So stars like Jupiter, planets like Jupiter and Saturn are present around 10% of low-mass stars that have been studied so far. Now, 1% of the stars have hot Jupiters. Remember, Jupiter is far away in the solar system. It's a very cold star because it's far away. It is a gas giant. We don't have a planet like Jupiter close to the Sun, say near the Earth. But in 1% of the stars that have been studied so far, there is Jupiter-like planet in short orbit. They will obviously be hot Jupiters. So let's say that there are two populations of Jupiter-like planets, hot Jupiter-like planets and cold Jupiter-like planets. Keep this in mind. The number of gas giant planets has a plateau in the middle around several astronomical units. So there are very few gas giant planets very close to the star and very few gas giant planets very far away from the star. In between, there is a plateau in the distribution. Most of them are in the region in between. There are fewer gas giants in very wide orbits. And here is something extremely interesting. There is a strong positive correlation between stellar metallicity and number of gas giants. Let me remind you once again what is metallicity. For astronomers, elements heavier than helium are metals. They are not metals, of course, but that's what astronomers call them. So there seems to be a strong positive correlation between heavier elements seen in the spectra of the stars and the occurrence of gas giants. Obviously, this has to do with the solid state chemistry of how planets actually form and the role of metal atoms in this condensation process. Remember, these are all things to keep in mind when you sit down and try to construct a theory. Here is another fact. There is an amazing number of close-in planets. They are smaller and they are low mass, like the Earth and Mars. There's a very large number of them. There is also a very large number of planets with mass between Earth and Neptune. They have orbital periods less than about 100 Earth days. This is something that I stressed earlier and showed 2 slides with data. So there is a very large number of what are called super Earths. So if you see in an article this word super Earth, they are referring to planets whose mass is between the mass of the Earth and the mass of Neptune. So its radius is between 1.5 times to 1.5 to 2 times the Earth radius to 3 to 5 Earth radius. They're a little bigger than the Earth. And here they are. Here is the fraction of planets observed as a function of the planet size. This one is the Earth. This is the Earth. And there is Neptune. And you see in between, where I put this arrow here, very large number, 520, 567. So there's more than 1,000 planets in this intermediate mass range where we don't have a planet like that, of that mass in our solar system. So here is another plot of that, is the average number of planets per star as a function of the planet size measured in Earth units. So again, you see sizes not seen in the solar system, sizes between the Earth and Neptune. So we have to understand why it is that in the solar system we don't have this, and yet in extra solar system there are a very large number of these already known. So here is another plot to stress this. These are the inner planets. This is the Sun, Mercury, Venus, Earth, Mars. And you see the same orbital region, which is the habitable zone, that is the green shading over there. You see planets which are quite big, which we don't find in the solar system. So these are the kind of constraints with which to test your theoretical ideas. Before we move on, here is our solar system. You all know about the planets. But I want to point out to you 2 features that you may or may not know. One of them you would know about, the asteroid belt between Mars and Jupiter. These are objects about 100 kilometers in size to smaller bodies. And then way beyond Pluto, there is what is known as the Kuiper belt objects. These were discovered by the Dutch astronomer Kuiper. Right? So that's where the solar system more or less ends. So the asteroid belt and the Kuiper belt objects are remnants of the early solar system from which planets did not form. Some objects form of the size of hundreds of kilometers, but they didn't go on to form large planets. So those objects are providing a very vital clue for our theoretical scenarios of how planets form from just gas and dust. All right. Here are the key steps in planet formation. When a star is formed, we don't yet have a clear picture of star formation. The idea is very simple. A molecular cloud is clobbered by a supernova blast wave, and there are many condensations and clusters of stars form. But the practical details are formidable. Rotation. You have to get into the angular momentum of the gas cloud which is collapsing, otherwise it will not collapse. Then it is a magnetic field which is getting amplified as it collapses due to flux conservation. The magnetic pressure might arrest the collapse. So there are a lot of difficulties in understanding. But what we do know observationally is that when stars do form in nature doesn't seem to have any difficulty in forming stars. It is surrounded by a disk which consists of gas and dust, and which we see in Alma observations and also in infrared observations. So here are the key steps in how to form planets like the Earth and Mars and Jupiter and Saturn, Uranus, Neptune, Pluto, and so on, starting with gas and dust. So the idea is that the disk of gas and dust around the star, which LaPlace had conjectured, which we see clearly with Alma and infrared telescopes, is the protoplanetary disk. It is this circumstellar disk from which protoplanets form, and then grow further to form planets of different masses and different sizes. So the basic tenet is that planets form in the gas-dominated disks. Now, as I said, Alma can resolve the largest of the disks, at least the outer regions of the disk. But what about the inner regions? They can also be routinely observed. They are being routinely observed by astronomers, either by direct imaging in the infrared. Why? Because dust will radiate predominantly in the infrared. So if you have an infrared telescope, like the James Webb Telescope, astronomers are dying to get their hands on James Webb Telescope for planet research, then you can directly image the inner regions, and in fact directly image the planets themselves through their infrared emission. Or if you cannot resolve it, what you try to do is to look at the infrared emission from the vicinity of the star. Sometimes you will find much more infrared emission than is expected from a star of a certain surface temperature. You know from Planck's law how much infrared you expect. If the infrared radiation you measure is far in excess of that, then you conclude from that there must be a disk in which there is gas and dust. Like in the case of accretion disks around black holes and neutron stars and binary systems, there is a donut-shaped distribution of gas and dust rotating around the central star. The evolution of the disk is determined, like in the case of accretion disks around neutron stars and black holes, by viscosity. It is viscosity which causes the matter in the accretion disk to flow radially inwards and finally accrete on to the central body, whether it is a neutron star or a black hole, in this case the host star. Different rings, if you can imagine the disk as composed of different rings rub against each other. There is friction, they lose angular momentum, and there is an inward flow of mass. But there is no accumulation in the disk. There is no piling up of matter in the disk. Therefore, m dot, the rate of inward flow, radial inward flow, must be the same at all radii. Otherwise, there will be a piling up, which we don't see. Now, the disk is not infinitely thin. It is puffed up. It is puffed up due to radiation pressure. Now, where is the radiation pressure coming from? Well, the central body, in this case the host star, is heating this gas, and therefore the gas has certain pressure, nKT, Boyle's law, and that pressure puffs it up. Obviously, the disk will be more puffed up near the star and be less puffed up far away from the star, just like around a neutron star or a black hole. So the physics of the protoplanetary disk is almost identical to the physics of the accretion disk around neutron stars and black holes. Fortunately for astronomers researching exoplanets, accretion disks around neutron stars and black holes have been studied extensively by theoretical astrophysicists for the last 30 or 40 years, and all that knowledge can now be brought to bear in this context. Now, the dust particles in the disk will collide against each other because there is friction, and sometimes they will stick. Why will they stick? Due to van der Waals forces. Right? This is how atoms become molecules. This is how molecules become dust grains of the size of a micron. And this is how micron-sized grains grow to become dust particles of the sizes of several millimeters or even larger. Now, this results in the formation of macroscopic planetesimals. So, the idea is, that is, the traditional hope was the following. Dust particle sticks, they form larger particles, and they become even larger and larger and larger. And finally, these aggregates of dust particles settle down to the plane of the disk. Right? We know in the case of our galaxy, most of the molecular gas and dust are in a thin disk about the plane of the galaxy. Somehow these aggregates, you started out with grains of the size of a micron, then they grew larger and they form aggregates, and these aggregates collide and form pebble-sized objects and even larger bodies. Eventually, these planetesimals, which are these larger bodies, may be of the size of 10 kilometers or even larger. At some stage, if you have in the disk objects whose sizes are 10 kilometers, they are massive enough that when they come close to one another, gravitational force between them becomes significant. And because of gravitational interaction, they come closer to one another and collide and coalesce. And there is a runaway accretion resulting in large asteroids. So that was the traditional hope. All right? Well, very reasonable thing. After all, you look out of your window, you see rocks and mountains. They must have all formed this way. Well, is it exactly this route or some other route? To verify that, you do computer simulation. Alas, when they did simulations, the simulations do not support this very simple hypothesis that I outlined in the previous slide. What they could find is that the maximum size of the particles they could form in that process was only about 1 millimeter or 2 millimeters in size. Because if you did form larger bodies, then by spallation, they are bombarded by smaller particles and so they break up again. Therefore, although larger bodies form, they also break up. Although particles collide and stick, they also break up, they also fission. So this simple idea doesn't seem to work. All right? Then somebody suggested, but look, if you have two types of particles in the disk going around the central star, one is the gas atoms and molecules, and the other are the dust particles, much larger in size. They may have different velocities. So there may be a difference in velocity between these two streams. And one of the things that we know from plasma physics and many other investigations is that whenever you have two streams, there can be instabilities. And these are called streaming instabilities. So according to current thinking, as of 2022, these streaming instabilities play a very vital role in the growth of the planetesimals, which eventually lead to the formation of the planets themselves. Now, these instabilities are driven by differences in the velocity of the motion of the gas and dust. Right? So there is gas going around the central star and there is dust going around the central star. Excuse me. They're going at slightly different velocities for reasons that I shall now explain. And it is that difference in velocity that gives rise to these streaming instabilities. So I've tried to read these papers. They're extremely complicated, and at some stage they depend upon simulations. So this is not something that I can work out, or you can work out the algebra and say, okay, now I understand this. So you have to do the simulations. So I will tell you what I have been able to understand with some pictures, because they are a lot more effective than writing equations, which may be too complicated for you, just as it was for me. So here is the central star, not to scale, and there is a disk of gas and dust around it, a flattened disk. Thickness of the disk very small compared to the size of the star. This gas disk consists mostly of hydrogen, and of course it has dust particles. Now both components should orbit the star in Keplerian orbits. So let's consider two dust particles shown over there. These two dust particles are going around the central star in Keplerian orbits. Fine. And so are the atoms and molecules in the disk. Now, as I shall now explain, the speed of the gas in the disk will be slightly less than what Kepler would want the gas molecules to have. But the gas particles will be very obedient to Kepler, and their velocities will be Keplerian. Now the question is, why are the atoms and molecules moving with speeds slightly less than what Kepler's laws tells them to do? And the reason is that the disk is not infinitely thin. It's a little puffed up because there is pressure. There is pressure because the radiation from the central star heats up this disk. The pressure of the gas in the disk will be given by Boyle's law, rho kT, where rho is the density. Now, if I plot the pressure and the y-axis here, and the radial distance along the x-axis, then since the inner regions of the disk will be hotter because it's closer to the star than the outer regions, there will be a radial gradient in the pressure. So the pressure of the gas will be slightly less as you go away from the star. Now, because of this pressure gradient, the gas in the inner regions of the disk will be moving slightly slower because remember, this pressure gradient is not in the vertical direction. That is also there. That's what causes the disk to puff up. But I'm talking about the radial gradient of the pressure. So gravity is trying to pull the molecules towards the star. But the pressure of the gas pressure gradient is trying to push the gas molecules away from the star. Therefore, gravity is partly offset. And therefore, the gas molecules are going at slightly sub-Keplerian speeds. All right? The inner portion of the disk, the pressure of the gas, the radial pressure gradient, not the pressure gradient. Remember our discussion of hydrostatic equilibrium when we discussed the stability of star. It is the pressure gradient which balances Gm rho over r squared. So same here. It is this radial pressure gradient. And so the gas is going slightly slower than the dust particle. So let us say for the purpose of illustration, these red particles are the dust particles. And the gray region is the gas, atoms and molecules. The dust particles themselves will be Keplerian because the pressure gradient doesn't act, because they are more massive, the pressure gradient is not going to offset any gravity. So the dust particles will have to obey Newton and Kepler. All right, so their velocities will be slightly Keplerian. Therefore, you notice the key thing here. There are two different velocities in the disk. The velocity of the molecules is slightly less, and the velocity of the dust particles is slightly more. That means they will rub against each other. As the dust particles rub against the gas, there will be a headwind. So there is no wind, but you are running, you are jogging in the morning. You feel a headwind because you are moving with respect to stationary gas. In this case, the dust particle is moving a little faster compared to the molecules which are also going around the central star. So the dust particle will feel a headwind, which will make it lose a certain amount of momentum, the circular velocity will decrease. As the circular velocity decreases, its angular momentum will decrease, and therefore it has to move in. Now here is the crazy thing. As the dust particle moves in, because it has lost some velocity, it will not go slower, it will actually go faster. Because when it comes inside, Kepler's law says, but now you have to go faster. So it will lose some more momentum and it will come in. So it will go faster and faster and faster. So it is again a case like negative specific heat in self-gravitating system. So remember, a satellite in low Earth atmosphere, because of the drag of the upper atmosphere, comes down. As it comes down, spiraling in, it's going faster and faster and faster, not slower and slower and slower. But it is coming in radially. That is what I have tried to indicate with these black arrows. So the dust particles are moving in radially because they are losing angular momentum due to the headwind. And the headwind is there because there is a relative velocity between the dust. Now, if the dust particles are losing momentum, that momentum has to go somewhere. That momentum is then given to the gas molecules. Therefore, the gas molecules will now go a little faster and it will be closer to the Keplerian speed. So, the dust particles loses energy, gas particles have to gain in energy. And as the gas particles begin to go faster, the headwind, the relative velocity between the gas and the dust becomes smaller. Therefore, this radial motion becomes smaller and smaller and smaller. So replay this video and listen to it again. So, as the dust particles slow down in their radial motion, because the differential velocity is decreasing, dust particles can coalesce and form clusters, such as this. Now these clusters will feel the effect of the headwind due to the gas and dust on these clusters will be even less. So if you're cycling, you feel less friction because you're moving slow. But if a big truck is going very fast, then it will feel an enormous friction because the headwind is there. But on the other hand, its mass is also larger. Therefore, the effective decrease in the momentum of the truck will be much less. Therefore, when these clusters of dust particles form, their radial motion inwards becomes less and less. And as these clusters drift in slower and slower and slower, they are joined by particles, isolated particles, which are moving in radially faster. So as these clusters are moving sluggishly, from the outer portion of the disk, dust particles are coming in radially because they are losing momentum to the gas, and due to friction, they are spiraling in. So eventually, there will be an exponential growth of this cluster. Such a cluster will grow exponentially to a very large size. And at some stage, they become large enough that self-gravity becomes important, and there is a gravitational collapse. Okay, so they become unstable against self-gravity. So planetesimals form, and detailed computer simulations show that there is no difficulty in forming in this two-stream instability, forming objects as large as 100 kilometers in size, which is the size of the bodies in the asteroid belt and in the Kuiper belt way outside. Now, these simulations also say something very interesting. What you find in these simulations is not only bodies of the size of 100 kilometers form, but they're invariably in binaries, two bodies going around each other in very tight orbits. And when you look not at the asteroid belt, but when you look at the Kuiper belt, which is beyond Pluto, there you find bodies which are mostly binaries. Therefore, these simulations give us exactly what we find in the Kuiper belt. So that gives us confidence in these simulations. Now, what simulations show is that certain locations within the disk may be preferred sites for these condensations and the formation of these very large bodies. One such preferred location is the vicinity of the snow line. All right? Snow line is the distance from the central star where water vapor condenses to ice. All right? At some distance, the temperature will be such that water vapor actually condenses to ice, to liquid water and then to ice. So that is one distance. So inside that snow line, as astronomers call it, there will be slightly different physics, and outside the snow line, there will be different physics because you have ice particles and condensations. The second is in the vicinity of 1 astronomical unit. What the simulation tells us is around 1 astronomical unit, which is the distance of the Earth from the Sun, some special things are happening. Now, strong support for the streaming instability comes from, as I said, Kuiper belt binaries. In the Kuiper belt, you find binary bodies. And what you find in computer simulations is binary bodies. So that gives us some confidence. Now, once planetesimals of the size of 100 kilometers form, they grow by mutual collisions. They collide and stick to one another. But they don't have to collide, because to actually collide, they must come within a distance which is smaller than the sum of the two radii. They don't have to touch each other because they're large enough so that here is one body, here is another body. As this approaches, it will be gravitationally deflected due to the gravitational influence of this body. This is known as gravitational focusing. This gravitational focusing increases the cross-section for collision. Why? A little thinking will tell you that this gravitational focusing factor is 1 plus v escape square divided by the square of the relative velocity between the two, and escape velocity is just 2 gm over r, just as the escape velocity from the Earth. The kinetic energy is equal to the potential energy. m1 and m2 are the two masses, and r1 and r2 are the two radii. So there are two things that come into effect. There is a relative velocity which will tell the bodies, don't stop, just go. The other one says, no, stick due to gravity. But then they can escape again. But in order to escape again, there is a certain velocity needed, minimum velocity, which is the escape velocity. So it is a competition between the escape velocity of the two bodies sticking together and the relative velocity near the closest approach. So this is the gravitational focusing factor. It is larger than 1 if the relative velocity is small compared to the escape velocity. Now, since the escape velocity is proportional to the mass, as the body grows, as the bodies go more and more massive, the gravitational focusing will become larger and larger, and the cross-section will not be simply pi r squared, which is the area, physical area of one body, but it will be much larger, is given by this. So what a little bit of thought will tell you is the rate of growth of mass is proportional to the cross-section. The cross-section is pi r squared. If there was no gravitational focusing, that the cross-section is increased enormously by gravitational focusing. Now, the radius of the planet will be proportional to m to the power 1 by 3 because mass is 4 pi by 3 r cubed into the density. Therefore, m is proportional to r cubed. Therefore, r is proportional to m to the power 1 by 3. Therefore, r squared is proportional to m to the power 2 by 3. Therefore, here is the beautiful thing. dm by dt, that is the rate of growth of mass, is proportional to the mass. So as the mass becomes larger and larger, the growth rate becomes larger and larger and larger. Therefore, there is an exponential growth due to positive feedback. There is a runaway growth. And that is how planets form. Well, but it's good to have some insurance. Even if this gravitational focusing is not that effective, you can resort to what astronomers now believe very firmly, which is known as pebble accretion. Pebbles are bodies, like planetesimals, which are large enough to be self-gravitating. So they are not like billiard balls. They are much larger than that. So they're just called pebbles. I don't know why, but they're just called pebbles. Now, planetesimals, which are embedded in the disk, which is made of gas and dust, can grow by accreting these pebbles. A planetesimal is formed. Its size is about 100 kilometers or 200 kilometers. Then there are these smaller bodies, and they can accrete and grow. They don't have to wait for another planetesimal to come nearby, get gravitationally focused and collide and coalesce. That can also happen. But then you have, it's like collecting a lot of raindrops that will fill your bucket. So similarly, even though these pebbles are small, a very large number of pebbles colliding with the planetesimal can make the planetesimal grow very fast if the planetesimal accretion is more efficient than accreting another planetesimal. Now, it turns out that the accretion of pebbles by protoplanets is more efficient than accreting another planetesimal, another protoplanet. And the reason is twofold. Number one, pebbles drift in the disk rather freely. Therefore, the original orbital neighborhood of the protoplanet will never be devoid of pebbles. In contrast, the radial drift of the planetesimals is negligible. Imagine you want two planetesimals to collide. So in the vicinity of one planetesimal, there has to be another planetesimal. And that has to come from some other radial distance. And how will it come? It has to lose angular momentum. But as it goes bigger and bigger, this headwind has less and less effect. So the radial motion of these planetesimals becomes very small, almost non-existent. Therefore, it is very unlikely that you will have another planetesimal coming to your neighborhood. But in any neighborhood, wherever the planetesimal is in the disk, the chances that it will be colliding with pebbles is very large because pebbles drift very freely. Since they are much smaller, the radial motion is not entirely arrested. The second is even more important. The cross-section for a protoplanet to capture a pebble is much larger than a cross-section for a protoplanet to capture another planetesimal. Let's try to understand this. Here is a protoplanet. Somehow it has grown to some size. And here is, it has a radius r and a certain mass. And let us say that there is a planetesimal. That planetesimal is gravitationally deflected. So you will expect the cross-section for this collision to be pi r squared, which is the cross-section, geometrical cross-section of this protoplanet, increased by this gravitational deflection. I told you, f of g is 1 plus square of the escape velocity divided by the square of the relative velocity. So that's what the cross-section is. It is increased just by this factor. But now let us consider the same protoplanet trying to accrete a pebble which is going at a very large distance, r subscript d. Now I maintain that the cross-section for this collision is really pi rd squared, which is a very large cross-section. Very large cross-section compared to this, which is only pi r squared increased by a small factor. Here, it's a very large distance. Why will this pebble be deflected at a large distance? Simply because its mass is very small compared to the mass of this. It will feel the gravitational influence. Now, let's try to pursue this further. As soon as the pebble gets deflected, its relative velocity will increase. Remember our low Earth orbit satellite rubbing against the thin atmosphere? It is losing velocity due to friction. As it loses velocity, it will go faster and not slower because it has to come in, and as it comes in, Kepler's law says that you have to go faster because gravity is stronger. Centrifugal force to balance gravity is mv squared by r, so it has to go faster. Therefore, the relative velocity between the gas and the pebble increases. As the relative velocity increases, it will feel more friction. It will lose more momentum and more energy. And so it will spiral in. So the pebble, the moment it gets deflected, instead of just going off, it will spiral in and finally accrete on to the protoplanet. Right? So this is why accretion by pebbles, accretion of pebbles is far more efficient. So you don't just, the gravitational focusing increases the cross-section substantially compared to a protoplanet accreting another large body. So this is why pebble accretion is very important. Now, if the mass flux of pebbles through the disk as they drift in radially, if the mass flux is large enough, pebble accretion can grow a moon-sized object to Earth masses within the lifetime of the disk, which is a few million years. So it is very easy to form a planet like the Earth or Mars or Venus by pebble accretion. There isn't very much gas surrounding the Earth or Mars or Venus. It's mostly solid body. And so pebble accretion is a very attractive possibility to form the smaller planets. Now, although many details are still not clear, at least that's the conclusion that I came to by trying to read these papers. But I also got the feeling that there is a very large consensus that pebble accretion is the dominant process in planet formation. So somehow you have to form a planetesimal, and then pebble accretion will allow you to form planets. So here is the snow line. Inside that you have rocks and metals condense. The hydrogen compounds like water vapor do not condense, they remain as vapor. But outside the snow line, there are not only rocks and metals which condense, but hydrogen compounds also condense, they form ice. Okay? So remember, 98% of the solar nebular material is hydrogen. Helium does not condense, okay, because of very large zero-point motion. Now, how do planets like Jupiter and Saturn form? They are gas giants. They are giants, presumably with a core, solid core, and then there is a very large envelope of gas. So this is what, pictorially, what astronomers seem to be converging on. First, there is a growth of solid core due to the accretion of planetesimals, but mostly due to the accretion of pebbles. So the core grows very fast due to pebble accretion. At some stage, there is a slow accretion of gas. And the gas is in hydrostatic equilibrium. Remember this picture? Exactly like when we discussed the stability of the sun and the stars. There is hydrostatic equilibrium. The gravitational force Gm rho over r squared is balanced by the pressure gradient. So a similar hydrostatic equilibrium will be there for this atmosphere. If the hydrostatic equilibrium is not there, all the atmosphere will collapse and condense onto the core itself. But it doesn't happen because of hydrostatic equilibrium. Then the core grows some more, and eventually it stops growing, and the gas accretion continues. The atmosphere becomes thicker and more extensive, and the atmosphere is still in hydrostatic equilibrium. And then the core growth stops, and hydrostatic equilibrium is suddenly lost. Why is hydrostatic equilibrium lost? What is hydrostatic equilibrium? dP by dr is equal to minus Gm rho over r squared, where P is the pressure. In the case of the sun, the pressure is due to the heat generated at the center by fusion reaction. Here, there is nothing happening in the planet itself. But because the core is hot, because it formed from hot material, there is a certain luminosity. This luminosity results in a pressure gradient which supports the gravitational force. And that is what hydrostatic equilibrium is. And when this core is no longer luminous, in other words, if the luminosity of the core drops to zero, then the pressure disappears, the pressure gradient disappears, and therefore there is nothing to support the atmosphere and hold it in hydrostatic equilibrium. There will be a runaway accretion of gas. So this is the scenario for formation of gas giants. So a planet like Jupiter or Saturn has a metallic core at the center, just like the Earth and Mars, but then it has a gigantic gas envelope, which formed due to runaway accretion. Let's try to understand this through actual calculational results. What is plotted on the y-axis is the mass in units of Earth's mass, and what is plotted on the x-axis is the age in millions of years. 1 million years, 2 million years, 4 million years, and so on. So what happens is that the core forms very quickly. The mass of the core grows very quickly to some 20 Earth masses, and then more or less remains the same as a function of time. The atmosphere grows. The atmosphere initially is in hydrostatic equilibrium. So the growth of the atmosphere is gradual and always in hydrostatic equilibrium. dP by dr is minus gm rho over r squared. But when the luminosity of the core disappears, there is a runaway gas accretion, and the mass of the gas shoots up. Remember, the y-axis is the mass. So the mass of the atmosphere originally was very small compared to the mass of the core, and then you find that the mass of the atmosphere increases exponentially. And therefore the mass of the planet itself, which is the sum of the masses of the core and the atmosphere, grows exponentially. And you have a gas giant like Jupiter. So to summarize, the picture is, when you're dealing with a terrestrial planet like the Earth, there is a formation of solid core by solid accretion, pebble accretion, and there is a very small amount of gas. When you come to the ice giants like Neptune, Saturn, and so on, then you have the formation of a solid core through accretion, and you have a slow growth of gas which condenses, and there is slow accretion. But when you come to a planet like Jupiter, there is gas accretion beyond a certain critical mass, there's a runaway accretion, and that's how gas giants form. This is the summary of the conclusions at the moment by astronomers working in this field. Let's skip that. So now I come finally to this topic of migration of planets. What you find is the size of planets related to Earth and y-axis as a function of the orbital period. So you have the large cold planets far away from the star, the cold gas giants like Jupiter, but you also have some hot Jupiter-like planets. So how did they move from there to there? That's an interesting question. So I shall try to tell you in few words what the current thinking is. Data suggests that planets migrate towards the host star, just as our gas molecules did, just as our dust particles did, just as our pebbles did. Planets also migrate. But you'll say, but wait a second, you told me that planetesimals don't migrate because they do not feel any significant headwind. That is true. But planets migrate for a different reason. And the reason is that simulations tell us that when a planet forms right there where the tip of the arrow is, it generates a spiral density wave in the disk. You see the spiral density wave very clearly. The color indicates the density contrast. All right? The spiral density wave is triggered by the planet embedded in a disk, and that is responsible for the formation of the spiral density wave. Now you may say, look, this is all computer simulation. I don't believe a word of it. Okay, look, here it is. This is an actual density wave, believe it or not, in the disk surrounding the planet Saturn, our Saturn, photographed by the Cassini spacecraft before it crashed into Saturn. You see the density wave, very beautiful density wave. And when you model this density wave from the data produced by spacecraft, what you get is a spiral density wave as shown in the bottom picture. So we don't have a Cassini photograph of the actual spiral density wave. It was too close to the disk to be able to see it. But computer simulations tell us that there is indeed a spiral density wave in the disk of Saturn. So you have to take this very seriously. A spiral density wave is generated by a planet that has already been formed. The exterior spiral density wave trails the planet. The angular velocity is smaller than the angular velocity of the planet, whereas the interior wave leads the planet. It's going faster. So there is differential rotation in any Keplerian disk. There must be differential rotation because the circular velocity is a function of the distance from the central gravitational body. Therefore, the gravitational attraction of the exterior wave on the planet exerts a negative torque on the planet. It's going slower. The planet is going faster. So therefore, there is a negative torque. The interior wave is going faster than the planet. So there is a positive torque. So the planet experiences both the slowdown torque as well as a spin-up torque. Now, what calculations tell us is that the negative torque due to the outside portion of the spiral density wave wins out, and the planet loses angular momentum, and therefore it moves radially in. Therefore, the planet migrates radially in due to the differential torques arising from the spiral density wave which it generated in the disk. Now, let me say it in the opposite direction. The planet exerts a positive torque on the outer portion of the disk and a negative torque on the inner portion of the disk. Previously, I said the disk exerts a torque. Now I'm saying the planet exerts a torque. So the sign will be reversed. The planet exerts a positive torque and on the outside and a negative torque on the inside. Now, in the case of the low mass planets, this torque is very, very small compared to the viscous torque that is making the matter in the disk flow radially inwards towards the star. Remember, there is a viscosity whose origin we do not understand, but gas moves in towards the star. So the gas is not bothered by the formation of the planets, but a spiral density wave forms. But if the mass of the planet is very large, like the mass of Jupiter or Saturn, then a gap appears in the disk, and the gas is pushed out in both directions. It is pushed out in the outer direction, it is pushed out in the inner direction. So there is a gap that opens up in computer simulations when the mass of the planet exceeds a certain critical mass. Is there any possible evidence for this? Well, here is a spectacular image produced by Alma, which shows a gap in the disk. Now, this gap in the disk is almost certainly due to a planet which has not yet been detected in the gap. So sooner or later, infrared James Webb Telescope observations hopefully will reveal a planet as being responsible for this gap in the outer portion of the disk around this particular star. So the formation, there is some evidence already of the formation of gap. Now, this planet will migrate inwards because of the torque exerted by the spiral density wave, and the gap will move along with the planet. So as the planet moves radially inward, the gap moves with it. Now, what calculations tell us is that the migration rate, the rate at which the giant planet moves radially in, seems to depend upon the viscosity of the disk. If the viscosity of the disk is larger, the migration rate is larger. If the viscosity is very small, then the migration rate is smaller. This may explain why most of the Jupiter-like planets or cold are not very hot. What I mean is, most of the Jupiter-like planets are at very large distances. They are very cold. They have not migrated to short distances. There are some, yes. This is now understood in terms of the relatively low viscosity. The way of saying this is, presumably the viscosity of the disk in our disk in the early solar system was low enough that the migration rate of Jupiter and Saturn was very, very small. That is why they are still way outside the Earth. But in the case of some disks, obviously the viscosity is very large, and you see that the giant planets have migrated to very short distances. So to conclude, I would say that on the observational front, the progress made in the last 25 years since the first discovery of the extrasolar planet has been nothing less than spectacular. And with James Webb Telescope soon to be released for observation, we expect great progress to be made. On the theoretical side, there has been great progress already in understanding how planets form, as well as why and how they migrate. But there is still much to be understood. What is extraordinary is, even though planetary systems have been found around 833 stars, there is not a single planetary system like our own solar system. So it looks like there may not be a simple global model that will explain the planetary system around all stars. So it's going to be a very complicated system. All sorts of possibilities are there, and all sorts of possibilities that are not forbidden will probably happen. So there is still much to be understood, but there is absolutely no doubt in my mind that the study of exoplanets, their formation and migration, is perhaps the most exciting frontier of astronomy today. It is an exciting frontier because great observational facilities are suddenly becoming available, in particular the James Webb Telescope. So with that, we shall conclude this discussion of exoplanets. And in the final series of lectures, I shall turn to a discussion of contemporary cosmology. Now, I have divided this discussion into a series of 6 lectures. In the next lecture, I shall discuss the expanding universe and the synthesis of elements when the universe was 3 minutes old. And in the next lecture, I shall discuss the architecture of the universe and its evolution. Then the evidence for the acceleration of our expanding universe. And then I shall discuss the Big Bang, what caused this explosive expansion of our universe. In the final lecture, or rather before that, I shall discuss the interplay between the macroscopic world and the microscopic world. Finally, we shall come to this grand question. Is there an universe with a capital U, the universe, or are there many universes, or is there a multiverse? So that's the plan for our discussion of cosmology. Till the next lecture, thank you very much for your attention.